Welcome back to Sustainable River Basin Management, the second part of Module 2, Part 1. Let's just have a look at what we have been doing and what we still have to do. We have completed Module 1, Concepts of Sustainability, and we have completed Week 1 of Module 2 on water resources and hydrological processes, and we are now starting with Week 2 on Module 2. The topics that we want to cover during this session is river and groundwater systems, stream morphology, land use, nutrient cycles, and ecosystem services. We'll start today with river and groundwater systems. Let's first of all start with the definition and the use definition of rivers. What we mean by river is a flowing watercourse, and when we talk about streams, we actually mean small flowing watercourses. Sometimes mix those terms loosely. A river is a primary carrier of fresh water usually, but we know that today we use our rivers as a drainage. We use it to offload waste and sewage. It used to be the primary source of drinking water and also the primary source for crop irrigation. We also use river as access points very much in the past to the hinterland, to enter our continents, and we use water courses as a transport way for people and goods still today. Most of these uses, which are so important and relevant, were most relevant before the Industrial Revolution and before we switched our economy to a carbon-based economy. So many of the uses are now defunct because of water pollution and of drying up of rivers. Rivers are not only what I've listed already, carrying water, but they also carry sediments, and by carrying sediments they carry nutrients. They are also habitat of aquatic and riparian life, and they connect different ecozones, such as, for instance, a mountain through floodplains to estuaries. And for that reason, we also call rivers as our lifelines. I don't want to go into all of the details on rivers because most of this you have heard in grade 6 in school already. So let's just look into some of the aspects which are relevant to water management and especially to the sustainability aspect. Let's start with river evolution. We have to acknowledge that rivers are very dynamic features. They change seasonally and they change their position, their flow long term. So for that reason they are often not good as country borders. And they also disappear or get destroyed by erosion and by tectonic processes and by repeated marine transgressions. So rivers come, change their location, change their flows, and eventually also disappear from the landscape. As one of the very highly dynamic features of river systems, we need to mention lakes and wetlands, and they are highly ephemeral water bodies, which means they fill up fast with sediments and or get disconnected from the source of water, and for that reason disappear from our landscape again. Although they are very important for ecological processes and very important for their biodiversity, especially for us. So traces of ancient river systems are found in today's sedimentary formations, and those sedimentary formations may form our today's aquifer systems. For instance, the Cuddalore Formation in South India. Let's look into an example that may be familiar to you, the Kaveri River in South India. And here we have a satellite image of 1984, Landsat TM image, just black and white here, showing us the Kaveri River here in blue. This is today's channel, and the Indian Ocean here in black. And we have various formations here, tertiary formations, which are very visible here, and sedimentary formations, grayish white, in those areas here between the ocean today. This whole picture has a width of about 56 kilometers. So those darker tones here in this sedimentary portion of the image are interchannel basins. They are composed of sandy clay and silt. And then we see lines here, which are in a lighter gray, whitish tone, which represent sandy textures. And from this we can see very clearly paleo channels of the Kaveri River. We can see those channels here, and we can see channels here, and we can see them here in between. We sharpen our eyes for that. So the letter C here indicates those former channels of the Kaveri River, which also the landscape has been worked and cultivated over so many centuries by farming communities. Still, those paleo structures are well visible on such images. And what we can also see is the old beach line in the dunes, which appear here as white sand formations here, very far inland today. This is one example where we can reconstruct the river evolution. And another interesting example is, I want to demonstrate you here, is the Zambezi River in southern Africa, one of the major river systems linking about 11 countries, where we can see the rejuvenation and river piracy, so-called the head erosion and tectonic uplift, and how this changes water systems entirely. Here we have southern Africa, and we have the major river systems and the familiar names here. Limpopo is one major river system today, is our Zambezi River and Okavango River that you also may be familiar with. And we see that all of those river systems, actually Okavango and Zambezi at that time, were captured by the Limpopo River, and the Limpopo itself formed a major delta at that time. When was that? This was during Mesozoic and Cenozoic times, and then major tectonic events took place, which then reversed flows and captured major parts of the Okavango River and channeled them into the today's Zambezi River. This map here shows us what we see today. This should be familiar to you. The Orange River, one of the few rivers draining into the Atlantic Ocean, and then the Okavango Delta, which became a terminal or a drunken delta in a desert region today due to these tectonic movements. So this is the situation since about Pleistocene time. So how do we know all this? This is known due to tectonic studies, first of all, seismic studies, geophysical studies, as well as ecological studies, where fish species occurring in these different rivers were compared, and where the separation of these river systems could be traced fairly accurately. Now, I want to stop at talking about rivers and come to the groundwater component, which in many cases has been forgotten or left out entirely. What we mean by groundwater is the water stored occurring in the underground, which continuously fills all of the spaces on our Earth's crust. And those spaces could be pores or fractures or bolts. We can envisage it in this way. We have minerals here. We may have particles composed of various minerals here, and then the spaces in between those dark spaces would be filled by water. The mobility and movement of the groundwater is determined by our Earth's gravity, and any flow occurs whenever there is a hydraulic potential. I don't want to go into more detail about this, as it's not relevant right now here. You may have seen or heard about underground river systems. Those occur and are also very important in some areas, but this is not called a groundwater. It's still a stream or a river, and managed accordingly and classified accordingly. Now, let's talk about the aquifer or groundwater-bearing rock formations. When we speak about groundwater, we do not include or define the properties or the origin of the water itself, and we're also not defining the rock formations in which this water occurs. And for that we use the term aquifer. So aquifer, rock formation that may be porous or fractured and store groundwater and are able to move, to allow groundwater movement. So they must be permeable for this to occur. Also, this definition is only relevant because of this condition. Aquifers must yield a significant quantity of water to wells or springs, so that it becomes useful for our water abstractions, for water management. Let's look into the groundwater recharge and yield that becomes important when you talk about aquifers. As I've said, any of these spaces in rocks or sediments which are not occupied by minerals are filled, and they are either filled by water or by gas, air for instance, in most of the cases, or by both of them. And that space is determined by a property called porosity or fracture system density. Now, not all of the water that is occurring in these spaces can be removed from these. And we call this water immobile water. And for that reason, we are not looking at porosity, the overall porosity of a rock or an aquifer. We are looking at the utilizable porosity, which is the pore space which is occupied by mobile water. That is water that can move through the aquifer, and it is water that can be abstracted in a well. This is what is relevant to us from a water management perspective. So that fraction of water which can be abstracted from the aquifer is called specific yield or storage coefficient. And that can vary for fractured aquifers around 0.05%, and in a very good aquifer reach up to 20%. So we have to keep in mind that only a fraction of the amount of precipitation reaching the surface transforms into a groundwater recharge. And only a fraction of this groundwater recharge we will be able to abstract from our aquifer system again. So this is very important to note when we talk about water budgets and how much water can be abstracted from a specific area. Important besides this are our groundwater recharge areas, and also let's look at basics to it. One of the occurring systems could look like this. We could have an aquifer, and that aquifer is covered by a layer of sand, something permeable. And Such an aquifer we call unconfined because local rainfall, local precipitation hitting the surface here can infiltrate and reach the water table and recharge this aquifer. We also call this a water table aquifer. So any rainfall here we can account for as a potential recharge to our aquifer. A different situation we have here where we have an aquifer and that aquifer is covered by a clay layer, for instance. It is covered by an impermeable layer. In such a case, we call confined aquifer, and in such a case, there cannot be any local recharge take place. So recharge must occur somewhere outside, distant from this box area of where we observe our aquifer and where we want to abstract water from. Now, this model here shows us how this occurs, and we have in this case a river system here. We have a permeable layer here, and an aquifer system which discharges water into the river, and the river itself also recharges the groundwater at some times. And then we have an impermeable layer here in between, and underneath this impermeable layer another aquifer system. Now we can access both of these aquifers from this point here. We can take water from the river, we can drill a well here and abstract water from here, or we can perforate the impermeable layer to reach the aquifer underneath and abstract water from there. However, we are not at this point recharging or able to recharge our aquifer system here. In this case, our recharge area is very distant from our point of abstraction. And this is very relevant for management purposes. If, for instance, there's an urban area that needs to supply water to its citizen, it may use those two aquifer systems, but the urban area itself may only be able to control and manage the upper aquifer, whereas to manage the resources of the lower aquifer, the management would have to focus on this area, which may be a mountain area or some other district, some rural area far away. Now, this is very important, and we will come back to this at a later stage when we talk about sustainable water management practices. Let's come back to and bring both river and groundwater together again in a system. And you have seen this before, and I want to stretch it here again. We have rainfall here, we have our evapotranspiration taking place, we have our runoff taking place, and then we have our internal catchment, internal processes taking place in various compartments, the unsaturated zone, the saturated zone, the stream network. Now, let's cover this part and only look at a situation where we have a rainfall event taking place. We have rainfall coming here, and we observe overland flow and monitor rivers. We have flowing rivers right now. If this is the case, then we can assume that either we don't have any aquifer system in our region, that we may have only impermeable layers in our particular area, or that our aquifer is fully recharged. Let's now imagine that our rainfall continues or increases in intensity. Our aquifers are fully recharged. or we don't have an aquifer, we don't have permeable layers here, then what we would see here is large inundations. We would see flood events taking place on our surface here. Now, if we take the opposite case, there's no rainfall at all taking place in this area, yet we still have rivers with water, flowing rivers. Then this can only take place when interflow occurs or when base flow takes place. So our groundwater systems are discharging into the river network. This groundwater may be coming from this local area where we have our monitoring station placed in our river. All this groundwater may come from a distant source and still discharge and contribute to our stream network. So what we need to conclude here is that, and take home, is that groundwater is not an additional source of water. It is not something that can be treated like an additional source, like the ocean water. It is connected to a river system, and the river system is connected to a groundwater. Both are interconnected. And whether a river discharges or recharges an aquifer may change seasonally in a particular region.